Okay, so we have the Laplace PE, and I forgot to use this symbol last time, but this thing here is the second derivative with respect to x plus second derivative with respect to y. And this has a name, it's called the Laplacian. So this equation here should be really thought as u second derivative with respect to x plus, when this hits this, it's u second derivative with respect to y, and x equals 0. Now in 3D, the Laplacian will be derivative xx, derivative yy, plus derivative zz. Okay? So that's the third dimension one. Last time we kind of reviewed all these vector calculus notations, and I talked about this notation called the upside down triangle. It's called nabla. So this one's called nabla. And this is, in 2D, it's partial with respect to x and then partial with respect to y. It's a vector of operators, so that if nabla is applied to f, you get the gradient, which is f differentiated by x and then f differentiated by y. That's called the gradient of f, right? But then if you take nabla dot of nabla f, then that would be nabla, well, nabla is derivative x, derivative y, dotted with this much is f differentiated by x and f differentiated by y. And because dot product means component-wise multiplication, you add them up. When this hits the first component, it's f second derivative, plus when this hits the second component, it's f two derivatives in y. So this is indeed the same as the Laplacian of f. So often in the literature, you'll see that instead of the Laplacian, this is called the, this is written as nabla dot nabla, or sometimes people just write it as nabla squared. Just like that. That's how they write that down the Laplacian. Okay, so that was just a notational explanation.